Hello everybody, I am Hamid Reza. First of all, I would like to extend my warmest wishes to you all on the beginning of the new teaching block. I am really delighted being with you as a lecturer for big data applications. It's my great pleasure to welcome you all to the class, or might be better to say, to the online class. In line with the government guidelines, the module will be delivered online until further notice. So in the meantime, please look after yourself and your family. Today, I first give you an overview of the module. After that, we will have a look at MapReduce and Hadoop. Let's start the module by looking at big data in practice, how 45 successful companies used big data analytics to deliver extraordinary results. The book contains a comprehensive collection of many real-life examples, from Apple to Facebook and Microsoft. I have listed some of the companies mentioned in the book. Walmart, as the first example, are the largest retailer in the world and the world's largest company by revenue. They plan to establish a big data platform to process 2.5 petabytes of information every hour. Walmart needs such a powerful platform to price goods and have them in the right stores once required. For the sake of better understanding, I explain how big 2.5 petabyte is by an example from the movie world. The average 4K movie with an average runtime of 2 hours is around 100 gigabytes of data. It means that 1 petabyte of storage can hold around 11,000 4K movies. So, it would take you over 2.5 years of non-stop binge watching to only go through the 11,000 4K movies with no analysis tasks. After this analogy, let's move from Walmart retail company to Shell, the fourth largest company in the world by revenue. It's estimated that Shell have generated around 46 petabytes so far through their data-driven oil field program to predict where to search for oil and hydrocarbon. Facebook users upload about 2.5 million pieces of content every minute to the site. The data is analyzed for clues to support targeted advertising. So, in the big data era, we highly rely on new technology to collect, store, and analyze such a tremendous amount of data and turn it into useful insights. It is interesting to know that 20 out of 45 companies investigated by MAR were using Hadoop and Spark to store and manage their tremendous amounts of data. Here we can see a list of companies that take advantage of Hadoop and Spark. Among them, we can see the name of gigantic tech companies such as LinkedIn, Facebook, and Netflix. You might ask why we need new tools for big data analytics, or why we don't use traditional tooling like SQL databases for data handling. To answer these questions, I should say that traditional databases are not scalable and consequently can't manage the huge volume of data. It's because they can't provide distributed data storage and distributed data management systems. That is why traditional data management tools are being replaced by scalable frameworks such as Hadoop, Spark, and other open source tools that allow big data processing to happen in parallel across thousands of distributed nodes. Here, we can see the syllabus covered in this module. We learn new programming models such as MapReduce and learn how to use big data platforms such as Apache Hadoop and Apache Spark to handle and analyze big data. We also have a look at machine learning with TensorFlow or deep learning, which is used in vastly different areas such as image processing, fraud detection, natural language processing, healthcare, etc. In this module, we will use the School of Computing Hadoop cluster to conduct practical sessions and labs. I will explain the machine's architecture later on. Each of you has an account to access the cluster through SSH or Jupyter notebooks. You must get the details of your account by now. If not, please let me know. If you have difficulties with Linux, don't worry. Please see Week 1 Practical on Moodle to learn how to connect the server through SSH. I skipped the following slides, presenting further details about the syllabus covered in this module, but you can go through them if you like. Now, it comes to assessment. The word assessment can cause anxiety in you. However, I really believe in your abilities, and I'm sure you will master very well what is delivered in this module. Your coursework represents 80% of the overall credit and will be a portfolio with 2 parts. The first part will be a lab book consisting of a record and reflection of the practical work you have been doing in the timetabled sessions throughout the term. The second part will be a report on an individual project you do in the later part of the term to practically learn the skills you have acquired earlier in the module. For further details, please have a look at Big Data Applications Coursework Word file on Moodle. In this file, you can find information about the deadlines, how to prepare your lab book, how to document your project, and the marking scheme. Presentations contribute to 20% of your grade. You are required to make a 10-minute presentation that provides an overview of the project you are doing in your coursework. Presentations will take place in the 2 last timetabled contact sessions of the teaching block. You can obtain further details at Presentation Assessment Word file on Moodle. In this file, the deadlines and the details about the presentations have been explained. It is important to note that the project topics should be determined by the 4th week of the teaching block. Here, I would like to appreciate Dr. Carpenter's efforts for designing and developing the module and thank him for his guidance and advice. Okay, let's start the module by MapReduce and Hadoop. Today, after reviewing the MapReduce programming model, we have a look at the essential features of Hadoop to run MapReduce applications. What is MapReduce? When the input data is large, the computation on the data have to be distributed across hundreds or even thousands of machines in order to finish in a reasonable amount of time. It's obvious that implementing such a parallel framework is not straightforward and includes complexities such as how to parallelize the computation, how to distribute the data, and how to handle hardware failures. To address these complexities, the MapReduce programming framework was introduced, which allows distributed processing of very large datasets. Here, I have listed the three main features of the MapReduce framework, encouraging big data users to use it. The first feature of the framework is its simple functional programming model. Users specify the computation in terms of two functions, named map and reduce. We will detail this programming model later on in the presentation. As the second feature, I want to point at the outstanding scalability of MapReduce. The framework automatically parallelizes the computation across large-scale clusters of machines. This automatic parallelization turns MapReduce into a highly scalable framework for handling big data. Since MapReduce is designed to help process very large amounts of data using hundreds or thousands of machines, the library must tolerate machine failures. This way, if computational tasks running on a node crashes due to the failure of the node, the tasks will be restarted on other nodes. Now, I want to present a brief timeline of MapReduce. In 2003, Google designed and implemented Google File System, a scalable distributed file system for large data-intensive applications. To meet the rapidly growing demands of its data processing needs, Google implemented MapReduce library, a new abstraction that hides the messy details of parallelization, fault tolerance, data distribution, and load balancing. Google implemented hundreds of its special-purpose computations using MapReduce library, including a rewrite of the indexing code used by Google search engine. While Google implemented MapReduce based on C++, a Java-based MapReduce released as Apache Hadoop in 2006. Okay, let's have a look at the MapReduce programming model in detail. To implement an application using MapReduce, users express computations by using two functions, map and reduce. The functions can be written in various programming languages such as C++, Java, Python, etc. At runtime, the framework first applies the map function to every line of input data, one by one, doing some initial processing. The function outputs some key value pairs as the results. Map tasks must be written in such a way that they can operate completely independently and in isolation on a single chunk of the overall larger dataset. In fact, there shouldn't be any dependency between mappers. Once the map step is completed, the reduce function is invoked to combine all values with the same key returned by the map function. We have here an example to clarify how MapReduce works. Consider the problem of counting the number of occurrences of each word in a large collection of documents. You can see the pseudocode for the map and reduce functions in this slide. The map function emits each word along with an associated count for occurrences which is 1 in this example. The reduce function sums together all counts emitted for a particular word. This slide shows how our word count application runs on a parallel machine. Suppose there exists an input document. First, the document is split between the workers. Since in this example the machine has 3 workers or nodes, the document is distributed between the 3 nodes. Then the map function is applied to each part. Here we can see the key value pairs returned by the map function. For instance, brown, 1 represents a pair. After that, the reduce function combines all the value with the same key. For instance, we have 2 pairs with the same output key value brown. The reduce function accumulates their values and outputs the pair brown, 2. As I just already mentioned, there are 2 main phases, map and reduce. But you can see here there is another phase named shuffling residing between them. The process of shuffling is used to transfer data from the mappers to reducers. In this process, each reducer gets 1 or more keys to process. The shuffling process ensures that MapReduce framework passes all the intermediate pairs produced by all mappers with the same output key to the same reduce invocation. This way, all occurrences of the same key are grouped together, and consequently, all data belonging to one key is located on the same reducer node. As shown here, all pairs with the same key values are grouped and sent to the same reducer. This slide details the overall flow of a MapReduce operation. The MapReduce framework automatically splits the input data and executes each partition on a node in parallel with the other partitions. For instance, in the word count example, documents are automatically distributed across multiple nodes, and on each node, the map function is invoked. After shuffling, the reduce function is invoked on some or all nodes to accumulate the map results. It should be mentioned the reduce operations is executed in parallel. As shown in the figure, the execution of MapReduce entails remote communications between nodes. We can take advantage of the MapReduce framework to process massive quantities of data in a highly scalable and fault-tolerant way. MapReduce applications are scalable since the data that cannot be stored in a single node is distributed between machines, and whole dataset never needs to be resident in memory. However, MapReduce is not suitable for iterative processing. You know that an iterative process is a process for calculating a desired result using a repeated cycle of operations. This figure here shows an iterative process that frequently calls map and reduce functions and stores the intermediate results in a distributed storage. Training an artificial neural network is an example of an iterative task. The training process is repeated until the desired accuracy is achieved. Even if iterative processing is implemented using MapReduce, it will be very slow because the results of each iteration should be stored in disks for each iteration. Storing a massive quantity of data in distributed disks generates a significant overhead and consequently degrades performance. After learning the basics of MapReduce, we want to study Apache Hadoop, a platform for running MapReduce programs. Apache Hadoop is a software or framework allowing the distributed processing of large data sets across clusters of computers using simple programming models. It's designed to scale up from single servers to thousands of machines, each offering local computation and storage. I want to give you a brief history of Apache Hadoop. Doug Cutting and Mike Caffarella looked for a way to build a web search engine from scratch. They released Notch, a working web crawler and search system, in 2002. But they found out Notch architecture cannot scale to the billions of pages on the web. By introducing Google's distributed file system in 2003, Notch developers used the file system to store the very large files generated as a part of the search crawl and indexing process. After releasing the MapReduce framework by Google in 2004, Notch algorithms were ported to run using MapReduce. Since Notch was applicable beyond the realm of search, in 2006, Notch creators decided to form an independent subproject called Hadoop. At the same time, Yahoo employed Mr. Cutting, and a month later, the company adapted Hadoop to build its internet-scale search engine. After that, much of Hadoop development has been led by programmers from Yahoo. It is interesting to know that the name Hadoop is not an acronym. In fact, Hadoop was the name of Mr. Cutting's son toy elephant. The Apache Hadoop software library includes three main modules. Hadoop Distributed File System, or HDFS, is a distributed file system that provides high-throughput access to applications' data across large clusters. Hadoop splits files into large blocks and distributes them across nodes in a cluster. It then transfers codes into nodes to process the data partitions in parallel. Hadoop Yarn is a framework for job scheduling and cluster resource management. This component brought to the framework from the second version of Hadoop. The computational engine is a component for the parallel processing of large datasets. Hadoop can run MapReduce applications or programs written in any other programming models. Some of you might have confused between Apache Hadoop and MapReduce. The table here compares Hadoop and MapReduce. Hadoop software provides a framework for distributed processing of big data across clusters using simple programming models. The core of Apache Hadoop consists of a storage part, known as the Hadoop Distributed File System, or HDFS, a resource manager, which is Hadoop Yarn, and a processing part which can be a MapReduce programming model. On the other hand, MapReduce is a programming model employed for processing and generating large data sets on clusters of computers. MapReduce is a method for large-scale parallelization using two functions named map and reduce. In a simple word, we use MapReduce framework to develop applications and use Hadoop to run our applications. Okay, let's go through HDFS, which is a scalable file system designed to store massive volumes of data across nodes in Hadoop clusters. HDFS has a master-slave architecture. An HDFS cluster consists of just a single master node named name node, which works as a directory service. In addition, each node in the cluster has usually a data node that manages access to all blocks of file data stored on the local node. In this slide, we can see the HDFS architecture for a cluster of two nodes, rack 1 and rack 2. Here we can see the single name node as master and data nodes for each node in the cluster. User data is stored in files and each file is split into one or more blocks. The green squares in the figure represents the block of files. These blocks are stored in a set of data nodes. The name node executes file system namespace operations like opening, closing, and renaming files and directories. It also determines the mapping of blocks to data nodes. The data nodes are responsible for serving read and write requests from the file system's clients. The data nodes also perform block creation and replication upon instruction from the name node. As we can see in this slide, the blocks of files are replicated for fault tolerance. Yet another resource negotiator, or YARN, is designed for cluster management and is one of the key features in the second generation of Hadoop. Like HDFS, YARN has a master-slave architecture. The master component in YARN is Resource Manager, which determines where and when requested containers will be run. Container is a place where a unit of work occurs. For instance, each MapReduce task runs in one container. So, a MapReduce application will run on one or more containers. Typically, there is one resource manager per Hadoop installation. The second component of YARN is the node manager. Each node in the cluster usually has one node manager that runs containers allocated to the node. In this slide, we can see the architecture of YARN using a cluster of 3 nodes. A resource manager keeps track of available nodes and their resources and performs resource allocation to containers. A node manager provides computational resources in forms of containers. We are not required to further detail the YARN architecture. To sum up, we studied the MapReduce programming model as a framework for parallel big data processing, which was introduced in the early 2000s. Apache Hadoop software library has been widely adapted to execute MapReduce applications. Although the popularity of MapReduce has declined over the last few years, Apache Hadoop has developed to support more processing models. As I mentioned earlier, during this module, we have access to the school Hadoop cluster. It consists of 13 nodes, including one head node and 12 workers. The head node runs Resource Manager and Name node. The workers each runs Node Manager and Data node. We have access only to the head node through the link shown here. In this slide, you can find some articles and books for further reading. Now, I invite you to watch a video summarizing what I talked about today. Thanks for your attention. Please contact me if you have any questions.
We all use smartphones, but have you ever wondered how much data it generates in the form of texts, phone calls, emails, photos, videos, searches, and music? Approximately 40 exabytes of data gets generated every month by a single smartphone user. Now, imagine this number multiplied by 5 billion smartphone users. That's a lot for our mind to even process, isn't it? In fact, this amount of data is quite a lot for traditional computing systems to handle. And this massive amount of data is what we term as big data. Let's have a look at the data generated per minute on the internet. 2.1 million snaps are shared on Snapchat. 3.8 million search queries are made on Google. 1 million people log on to Facebook. 4.5 million videos are watched on YouTube. 188 million emails are sent. That's a lot of data. So, how do you classify any data as big data? This is possible with the concept of 5 V's: volume, velocity, variety, veracity, and value. Let us understand this with an example from the healthcare industry. Hospitals and clinics across the world generate massive volumes of data. 2,314 exabytes of data are collected annually in the form of patient records and test results. All this data is generated at a very high speed, which attributes to the velocity of big data. Variety refers to the various data types, such as structured, semi-structured, and unstructured data. Examples include Excel records, log files, and X-ray images. Accuracy and trustworthiness of the generated data is termed as veracity. Analyzing all this data will benefit the medical sector by enabling faster disease detection, better treatment, and reduced cost. This is known as the value of big data. But how do we store and process this big data? To do this job, we have various frameworks such as Cassandra, Hadoop, and Spark. Let us take Hadoop as an example and see how Hadoop stores and processes big data. Hadoop uses a distributed file system known as Hadoop Distributed File System to store big data. If you have a huge file, your file will be broken down into smaller chunks and stored in various machines. Not only that, when you break the file, you also make copies of it, which goes into different nodes. This way, you store your big data in a distributed way and make sure that even if one machine fails, your data is safe on another. MapReduce technique is used to process big data. A lengthy task A is broken into smaller tasks, B, C, and D. Now, instead of one machine, 3 machines take up each task and complete it in a parallel fashion and assemble the results at the end. Thanks to this, the processing becomes easy and fast. This is known as parallel processing. Now that we have stored and processed our big data, we can analyze this data for numerous applications. In games like Halo 3 and Call of Duty, designers analyze user data to understand at which stage most of the users pause, restart, or quit playing. This insight can help them rework on the storyline of the game and improve the user experience, which in turn reduces the customer churn rate. Similarly, big data also helped with disaster management during Hurricane Sandy in 2012. It was used to gain a better understanding of the storm's effect on the east coast of the U.S., and necessary measures were taken. It could predict the hurricane's landfall 5 days in advance, which wasn't possible earlier. These are some of the clear indications of how valuable big data can be once it is accurately processed and analyzed. So, here's a question for you. Which of the following statements is not correct about Hadoop Distributed File System, HDFS? A. HDFS is the storage layer of Hadoop. B. Data gets stored in a distributed manner in HDFS. C. HDFS performs parallel processing of data. D. Smaller chunks of data are stored on multiple data nodes in HDFS.